Imagine standing outside on a clear night beneath the dark sky. Instead of tracing a map of established facts and labeled stars, imagine the darkness as a vast canvas of open questions. There is a quiet beauty in not knowing. The unsolved mysteries of the cosmos do not demand our immediate answers. Instead, they offer a space for our minds to wander and rest, a gentle reminder that we are part of something much larger than ourselves. Tonight, we will explore 50 of the deepest riddles that continue to puzzle science, choosing to appreciate the silence of the unknown rather than rushing to solve it. Welcome to Sleepy Mind Lab. Get comfortable, let go of the day, and let your thoughts drift into the quiet corners of the universe. Let us journey back to the very beginning, to a moment before time itself was born. Before the Big Bang. If we travel back through the history of everything, we eventually run into a wall. We call this wall the Big Bang, a moment 14 billion years ago when everything in our universe was squeezed into a space smaller than a single grain of sand. It is tempting to ask what was happening the day before this event, but asking what came before the Big Bang might be a question that does not make sense. The physicist Stephen Hawking suggested that asking what lies before the beginning of time is exactly like asking what lies north of the North Pole. If you stand on the very top of the world and ask to go further north, you cannot do it. There is no direction to take because the coordinate system itself ends at that point. In the same way, time itself may have started at the Big Bang, meaning there was no before. Yet, this explanation does not satisfy our desire for answers. When we try to use our best mathematical tools, like general relativity, to understand the very beginning, the equations break down. They give us infinite density and infinite heat, a point called a singularity. When math points to infinity, it is usually telling us that we are missing a piece of the puzzle. The rules we use to describe gravity do not work when things get that small and heavy. We need a new way of thinking about the cosmos. Some scientists suggest that our universe did not start from nothing. Instead, they propose a concept called a quantum bounce. Consider a balloon that you squeeze until it cannot get any smaller, and then it suddenly springs back outward. Perhaps our universe was once vast, collapsed down under its own weight, and then bounced back, starting the expansion that is happening today. If this is true, then time did not start at the Big Bang. There could have been an infinite line of past universes, each bouncing into the next, stretching back forever. Another idea is that time is like a clock that has no hand for 12. You can get closer and closer to the start, but you can never actually touch the exact moment of beginning. It is like trying to find the smallest fraction greater than 0. You can say 1 over 10, 1 over 100, or 1 over a million, but you will never reach the absolute starting point. There is always a smaller fraction, a moment just a little bit closer to the beginning. We are left with a quiet mystery. Was the start of our universe a true beginning of time, or was it simply a transition from another state that we cannot yet perceive? As we drift off to sleep, we contemplate that ancient fire, still searching for the moment the clock began to tick. Cosmic inflation trigger. Consider a balloon. Imagine this balloon starts smaller than a single atom. Then, in a tiny fraction of a second, it swells to become larger than our entire galaxy. This is the scale of change scientists call cosmic inflation. It is a moment when the early universe expanded at a speed that defies our everyday understanding of physics. The sheer rate of this growth is difficult to comprehend. It stretched the fabric of reality itself, smoothing out any wrinkles and creating the vast, uniform canvas we observe today. For a very brief moment, space itself stretched faster than the speed of light. To explain this sudden growth, scientists proposed a special kind of energy field. They call it the inflaton field. We can think of it as a quiet force that briefly filled every corner of existence. The particle associated with this field, the inflaton, is still a mystery. We do not know what it looked like or how it behaved. The biggest puzzle is the trigger. What caused this field to suddenly activate? If the universe was quiet and small, what spark set off this massive expansion? We have theories, but no solid answers. It is as if a quiet room suddenly erupted into a deafening roar without any warning or cause. We are left to contemplate what initial push set the cosmos on its path. Even more puzzling is how this expansion ended. If the universe kept expanding at that speed, stars and planets could never have formed. The gravity of matter would never have been strong enough to pull things together. Space would be empty, cold, and dark forever. We would not be here to ask these questions. Instead, the inflation stopped. Think of a runaway train traveling at speeds we cannot even comprehend. Suddenly, without crashing, this train slows down and comes to a gentle stop at a station. The energy that was driving the expansion did not vanish. It transformed. It decayed into the hot soup of particles that eventually became stars, galaxies, and eventually, us. Why did the inflaton field lose its strength? What caused it to decay at that exact moment? If it had lasted a fraction of a second longer, the universe would be too dilute for life. If it had ended too soon, the universe would have collapsed back in on itself. We do not know what mechanism acted as the brake. The trigger that started it, and the mechanism that stopped it, remain silent. We are left looking back at the beginning of time, staring at a sudden burst of creation, and wondering what quiet hand turned the switch on, and then, just as quickly, turned it off. The Hubble Tension. Imagine you have a wooden kitchen table. You want to measure its length, so you reach for two different measuring tapes. Both tapes are brand new, crafted by the finest toolmakers in the world, tested to be precise down to the width of a single hair. You lay the first tape down, and it tells you the table is exactly 6 feet long. You lay the second tape down, and it tells you the table is 5 feet and 9 inches. You measure again and again. Both tapes are flawless, yet they disagree. This is the quiet, nagging mystery currently keeping astrophysicists awake in the quiet hours of the night. It is a puzzle known as the Hubble Tension. For decades, we have known the universe is expanding. Galaxies are rushing away from one another, stretching the fabric of space. The rate of this expansion is a number called the Hubble constant. To find this number, scientists observe the cosmos in two different ways. The first way is to study the very beginning of time. We study the cosmic microwave background, which is the faint, fading heat left over from the Big Bang. This light has been traveling through space for over 13 billion years. By studying this ancient glow, we can calculate how fast the universe should be expanding today. It is like studying an early childhood photograph of the cosmos and using the laws of physics to predict how tall it will grow when it is an adult. This method tells us that space is expanding at a speed of about 67 kilometers per second for every megaparsec of distance. The second way is to measure the current universe directly. We study special stars called Cepheid variables. These stars pulse with a regular rhythm, acting like cosmic light bulbs of known brightness. By measuring how bright they look to us, we can calculate exactly how far away they are. When we combine this distance with how fast they are moving, we get a direct measurement of the expansion today. This method is like using a physical tape measure on the universe right now. But this method gives us a speed of about 73 kilometers per second. These two numbers, 67 and 73, might seem close, but the precision of our modern instruments means they should overlap. Instead, they stand apart, refusing to meet. Think of two trains traveling toward each other from different cities. Both train conductors have perfect clocks and follow their schedules precisely. Yet, when they reach the station, their arrival times do not match. The clocks are not broken, and the tracks are clear. The only explanation is that there is a route, or a speed limit, or a shortcut that the conductors do not know about. This discrepancy suggests that our picture of the cosmos is incomplete. We might be missing a fundamental piece of physics. Perhaps dark energy changes over time, or some undiscovered particle is altering the speed of space. The tension is a gentle reminder that our maps of reality still have blank spaces. Dark matter identity. Imagine standing on the edge of a deep forest late at night. The air is still, but suddenly you notice the leaves shaking. The branches bend and sway. You feel the cool brush against your skin. You know the wind is there because of its effects, but the wind itself remains invisible. This is very similar to how astronomers study our universe. We observe the deep dark of space and find stars moving faster than they should. We observe entire galaxies spinning rapidly, holding together when they should be flying apart. Without some extra gravitational glue, these massive collections of stars would have torn themselves apart billions of years ago. Something invisible is pulling on them with immense gravitational force, keeping them locked in their orbits. We call this mysterious substance dark matter, and it is one of the greatest puzzles in modern science. Every single thing we have ever touched, experienced, or measured on Earth and in the stars, from the water we drink to the hot plasma of the sun, is made of normal matter. This includes all the planets, the vast clouds of interstellar dust, every glowing nebula, and every star in every galaxy. Yet, when we add all of this up, all of this normal matter makes up only 5% of the cosmos. The rest of the material universe is dark matter, representing 85% of all the matter that exists. We are living in a universe where the vast majority of reality is made of something we cannot even identify. For decades, scientists have been searching for the identity of this invisible weight. One leading idea is that the universe is filled with weakly interacting massive particles, often called WIMPs. These would be heavy particles that pass right through normal matter, rarely leaving a trace. Millions of them could be passing through your body every second without you ever feeling a thing. Another major candidate is an extremely light particle called the axion, which could behave more like a wave spreading through space, flowing across the universe in vast, silent streams. To catch these elusive ghosts, we have built some of the most sensitive detectors ever created. We have placed them deep underground, buried beneath miles of rock in old gold mines and beneath mountains to shield them from cosmic rays. These detectors are filled with liquid xenon or supercooled crystals, waiting for a single dark matter particle to bump into an atom and create a tiny flash of light. Yet, year after year, these highly sensitive machines remain completely silent. We listen to the quiet depths of the Earth, but we hear nothing. We are searching for the wind, but we have not yet touched a single breeze. We know it is there, shaping the cosmos, but its true identity remains hidden in the dark. Dark energy source. We once believed the vast stretches of space between galaxies were completely empty and quiet. We imagined a peaceful void, a silent stage where gravity slowly pulled stars and galaxies together. We now know this emptiness is alive with a strange pressure, actively pushing galaxies away from one another. Instead of slowing down under the pull of gravity, the expansion of our universe is accelerating, moving faster with every passing moment. We call this mysterious influence dark energy, yet naming it does not mean we understand it. It makes up roughly 68% of everything in existence, yet its origin remains one of the deepest secrets of the cosmos. We cannot see it, we cannot touch it, and we cannot measure it directly. We only know it is there because we see the galaxies fleeing from each other. Albert Einstein once suggested a concept known as the cosmological constant. He proposed that empty space is far from nothingness, instead possessing its own inherent energy. In this view, as more space comes into existence, more of this vacuum energy appears to fill it. This constant energy maintains a steady density, acting as a repulsive force that never dilutes, no matter how large the universe grows. It is a fundamental property of space itself, a quiet tension woven into the fabric of reality. Imagine a rubber band that, instead of resisting as you pull it, actually pushes outward to assist the stretch. The vacuum of space seems to do just that, generating a quiet pressure that grows stronger as the distance between galaxies increases. Some thinkers propose a different explanation called quintessence. Instead of a static property of space, they suggest a dynamic energy field that fills the universe. This field would flow and change over time, perhaps strengthening or weakening across cosmic history. If quintessence is real, it behaves almost like a fifth force of nature, adjusting its grip on the universe as the eons pass. It could have been weak in the early universe, allowing gravity to pull matter together to form the first stars, only to wake up later and begin pushing everything apart. This idea suggests that the force driving the cosmos is a living, evolving presence, rather than a fixed law. The true nature of this force will shape the ultimate destiny of everything we observe. If it remains constant, galaxies will eventually drift so far apart that their light will no longer reach us, leaving our Milky Way alone in a cold, dark void. The night sky would eventually become completely black, devoid of distant starlight. If it grows stronger, it could eventually tear apart galaxies, stars, and even atoms in a final, silent event. We find ourselves living in a brief, golden window of cosmic history, where the stars are still visible, and we can still contemplate the deep night to ask what pushes the cosmos apart. We are left to watch the slow retreat of the stars, wondering what quiet power flows through the emptiness. Matter, antimatter, asymmetry. Why are we here at all when the math says everything should have dissolved into pure light? This question lies at the very heart of our existence. When we look out at the cosmos, we see stars, planets, gas clouds, and galaxies, all made of regular matter. We see the ground beneath our feet, and we feel the air we breathe. It all seems perfectly normal. Yet, according to our best scientific equations, none of this should be here. The universe should be completely empty, a vast and quiet dark space filled with nothing but fading radiation. To understand why, we have to look back to the beginning of time. In the first moments of the Big Bang, the universe was a dense, hot soup of energy. As this energy began to cool, it transformed into particles of matter. Nature operates with a rule of symmetry. For every single particle of regular matter that was created, an antimatter mirror image was also born. If you have an electron, you must also have an anti-electron, which we call a positron. They are identical in almost every way, except they carry opposite electrical charges. This opposite nature creates a problem. When a particle of matter meets its antimatter twin, they instantly destroy each other in a flash of energy. This process is called annihilation. During the very early stages of the cosmos, the universe was crowded with these particles, constantly colliding and destroying each other. It was a cosmic game of musical chairs where every player had a partner, and when they met, both vanished into light. If the symmetry was perfect, every single particle of matter would have found its antimatter match. They would have cancelled each other out completely, leaving behind a universe made of nothing but light. Yet, we are here. The stars shine, and the planets orbit. Somehow, some matter managed to survive the Great Destruction. Scientists have calculated that for every 1 billion pairs of matter and antimatter particles that collided and destroyed each other, a single, lonely particle of regular matter was left over. This tiny asymmetry, one extra particle in a billion, is the reason everything we know exists. It is the raw material that went on to form the first atoms, the first stars, and eventually, us. Why did this tiny imbalance exist? What favored matter over antimatter in those first crucial moments? Physicists have searched for answers in giant particle accelerators, trying to find some fundamental difference in the way these particles behave, yet the discrepancy remains unexplained. We are the leftovers of a cosmic battle that should have ended in a draw, living in a universe built from the survivors of a mystery we still cannot solve. The Singularity Core. Imagine a star dying. A giant star, many times larger than our Sun, running out of fuel. It collapses under its own immense weight, falling inward, heavier and heavier, smaller and smaller, until it crosses a threshold where gravity becomes absolute. At the very center of this collapsed star lies the singularity. General relativity, our best theory of gravity, tells us that all the mass of this giant star is squeezed down into a point of zero volume. Think about that for a moment. An infinite amount of matter packed into a space that has no height, no width, and no depth. It is a place where density becomes infinite, and the curvature of space and time becomes infinitely sharp. This is where our understanding of reality begins to tear. In our daily lives, we deal with things that have size and shape. A grain of sand is small, but it still takes up space. If you divide it, the pieces still have volume. A tiny dust mote floating in a sunbeam still has a physical boundary. But general relativity insists that at the heart of a black hole, space itself has been crushed out of existence, leaving behind only a point of infinite heaviness. If you were to travel to this point, you would find no surface to land on, no physical object to touch. There would be only the sheer weight of a giant star concentrated into absolutely nothing. Yet, when we look at this through the lens of quantum mechanics, the science of the very small, we run into a wall. Quantum physics tells us that nothing can be pinned down to a single, infinitely small point. The universe has a limit on how precisely we can know the position of any particle, and there is a minimum scale of length, known as the Planck length, beyond which space cannot be divided. According to quantum laws, a point of zero volume is impossible. The quantum world is inherently blurry, filled with jittering particles that refuse to be squeezed into a perfect, absolute zero. So we have two brilliant theories, each tested and proven right 1,000,000 times over, saying completely opposite things about the exact same spot in the universe. One theory demands an infinite point, while the other forbids it. This mathematical collision is far more than a minor disagreement. It signals that our physics is incomplete. The singularity is a signpost pointing toward a deeper, undiscovered law of nature, a theory of quantum gravity that we have yet to write. Until we find that theory, the core of a black hole remains a blind spot, a place where gravity and quantum mechanics stand in silence, refusing to speak to each other. But what if the mystery lies at the center, and also at the very boundary of no return? The Event Horizon Paradox. Imagine holding a paper diary in your hands, filled with handwritten notes, thoughts, and memories. If you throw this diary into a fireplace, it burns. The paper turns to ash, the ink vaporizes, and the heat escapes into the room. To our eyes, the words are gone. Yet, if you had a supercomputer that could track every single atom of smoke, every speck of ash, and every wave of light that escaped the flames, you could theoretically reconstruct the diary. The information is not gone. It is simply scattered, scrambled into a state that is too chaotic for us to read. In the language of quantum physics, information is never destroyed. It is conserved, surviving in the messy details of the universe. Now, imagine carrying that same diary to the edge of a black hole and letting it fall past the event horizon. This is the boundary of no return. Once the diary crosses this invisible line, it cannot send any signals back. But for a long time, physicists believed the information was still safe inside, simply locked away from our sight. This comforting idea was disrupted in the 1970s when the physicist Stephen Hawking made a startling realization. Using the rules of quantum mechanics, he discovered that black holes are not completely black. They slowly leak energy. Over vast stretches of time, tiny particles emerge near the event horizon, stealing a tiny bit of mass and radiating away into space. This process, known as Hawking radiation, means that a black hole will eventually shrink and completely evaporate into nothing. This creates a profound paradox. If the black hole disappears, what happens to the diary that fell inside? The radiation coming out is completely random. It does not carry the memories written on the pages. If the black hole evaporates completely, the information seems to be erased from existence. This leads to a direct clash between two pillars of modern physics. On one side, general relativity describes gravity and tells us that anything crossing the event horizon is trapped and eventually gone when the black hole vanishes. On the other side, quantum physics states that information can never be destroyed. If information can be lost, then the laws of physics do not work. The past cannot be reconstructed, and the future cannot be predicted. Physicists have spent decades trying to resolve this conflict. One of the most strange proposals is the holographic principle. This idea suggests that the three-dimensional world we experience, including the inside of the black hole, might be an illusion. Instead, all the information about the diary is encoded on the two-dimensional surface of the event horizon, much like a hologram on a flat credit card. As the diary falls in, its information remains stored on the outer boundary, escaping into the universe as Hawking radiation leaks away. This suggests that the boundary of a black hole is a crowded storage space rather than an empty doorway. It raises a deep question. If the universe stores its secrets on its boundaries, is our entire reality just a projection from a distant, flat screen? The boundary of a black hole forces us to question the nature of space itself, leaving us to contemplate whether our solid world is as real as it seems. The Fermi Paradox. Imagine standing outside on a clear, quiet night, with the dark sky stretching out above you. Above you are thousands of stars, each one a distant sun, many of them far older than our own. If we expand our view to the entire Milky Way galaxy, the numbers become hard to wrap our minds around. There are hundreds of billions of stars swirling in this vast spiral. Scientists estimate that billions of these stars host planets similar to Earth, worlds that sit in the zone where liquid water, and perhaps life, could exist. Since our universe has been around for nearly 14 billion years, many of these worlds had a head start of millions, or even billions of years, before our own home planet even began to form. With so much time and so many opportunities, the question remains, where is everyone? This simple question is known as the Fermi Paradox. If the universe is crowded with planets, and even a tiny fraction of them developed intelligent life, the galaxy should be teeming with signs of technology. Even at our current, relatively slow rate of space travel, a civilization could travel to and colonize the entire galaxy in a few million years. In cosmic terms, a few million years is just a brief moment. Yet, when we point our telescopes into the deep dark of space, we hear nothing. No radio signals, no giant cosmic structures. We are met with an unexpected and profound silence. To explain this silence, thinkers have proposed the concept of the Great Filter. This idea suggests that there is some nearly impossible barrier that prevents life from developing into an advanced spacefaring civilization. This barrier could lie in our past. Perhaps the transition from simple single cells to complex organisms is so rare that we are one of the very few to ever achieve it, meaning we have already passed the hurdle. Or the filter could lie in our future. It might be that civilizations naturally destroy themselves shortly after they discover powerful technologies, like nuclear energy or artificial intelligence. If that is the case, the cosmic silence we observe is the quiet aftermath of others who failed to cross that final boundary. Alternatively, the silence might be a deliberate choice. Perhaps they are out there, quietly watching us from a safe distance, choosing not to interfere with a young species, much like humans observe animals in a nature reserve. Or maybe space is simply too vast, and the distances between stars are too great for any two civilizations to ever make contact. We are left with two equally profound possibilities. Either we are completely alone in this vast, dark ocean, or the universe is full of life that is actively hiding from us. Both ideas invite us to sit quietly with the mystery, contemplating the stars and appreciating the rare and quiet beauty of our own existence. The Great Attractor. Imagine a vast, dark current flowing through a silent, pitch-black ocean. In this ocean, thousands of ships are drifting, but they are not floating aimlessly. Instead, they are all being drawn slowly and steadily toward a single, invisible whirlpool hidden deep in the shadows. No matter how much the captains try to steer away, the current carries them forward. This is the reality of our home in the cosmos. Our galaxy, the Milky Way, along with thousands of other nearby galaxies, is sliding through the darkness. We are traveling toward a mysterious, unseen destination. Scientists call this gravitational hotspot the Great Attractor. It is located hundreds of millions of light years away, nestled in a region of space that remains obscured. We know it is there because we can feel its pull, and we can observe other galaxies responding to it. Our galaxy is rushing toward this point at a speed of about 600 kilometers per second. That is over 2 million kilometers per hour. We are moving very fast, yet we cannot see what we are racing toward. We are simply pulled along by a cosmic gravity that we cannot measure directly. The reason for this mystery lies in the structure of our own galaxy. When we peer into the night sky, we are peering through the disk of the Milky Way. This disk is filled with thick clouds of cosmic dust, gas, and countless stars. This dense wall of matter creates a blind spot that astronomers call the zone of avoidance. It blocks our view of about a fifth of the universe, and the Great Attractor sits right behind this thick galactic fog. It is as if we are traveling down a dark road in a heavy fog, feeling a strong wind pushing our car to the side, but unable to see what lies beyond the tree line. Because of this cosmic blind spot, we cannot get a clear picture of what is actually pulling us. Is it a massive cluster of galaxies, far larger than anything we have ever discovered? Or is it something else entirely, a concentration of mass that we do not yet understand? We have used special telescopes that can peer through some of the dust using infrared and radio waves, but the full picture remains hidden. We only see hints of massive structures, but nothing large enough to explain the immense pull. The mystery remains. We continue to drift, pulled by an unseen force, traveling through the dark toward a destination we may never fully see. Cosmic neutrino background. As you sit in the quiet of the night, a silent, invisible wind is blowing straight through you. Every single second, trillions of tiny, ghostly particles pass through your body, your room, and the entire Earth, leaving absolutely no trace. They travel at nearly the speed of light, carrying ancient secrets from the very beginning of time. These particles are neutrinos, and they have been traveling across the cosmos for billions of years, untouched and unchanged. We are familiar with the cosmic microwave background, which is the oldest light in the universe. That light began its journey about 380,000 years after the Big Bang, when the universe finally cooled enough for light to travel freely. It is a beautiful baby picture of our cosmos. But there is an even older relic hidden in the darkness. The cosmic neutrino background was released when the universe was only 1 second old. If we could detect these ancient particles, we would have a picture of the universe when it was just a tiny, hot baby, long before the first stars or galaxies were born. The challenge is that neutrinos are like ghosts. They barely interact with normal matter. A single neutrino could travel through a block of lead, a light year thick, and never hit a single atom. To these particles, the solid ground beneath your feet, the walls of your house, and your own body are as transparent as empty space. Because they interact so weakly, capturing them is one of the greatest challenges in modern physics. We build giant detectors deep underground, filled with thousands of tons of water or heavy fluids, just hoping to catch the tiny flash of a single neutrino colliding with an atom. But these detectors only catch the high-energy neutrinos from the sun or distant exploding stars. The ancient neutrinos from the cosmic background have cooled down over billions of years. They are now extremely cold and have very little energy, making them almost impossible to detect with our current technology. If we could somehow build a net fine enough to catch these low-energy relics, we would unlock a door to the absolute beginning of time. We would map the universe as it existed in its first second of life. We would understand how the hot soup of early particles began to clump together to form the seeds of everything we see today. Until then, this ancient, ghostly wind continues to stream through us in the dark, a silent witness to the dawn of creation, waiting for us to find a way to listen. The axis of evil. Think of the oldest light in the cosmos, a faint glow left behind from the very beginning of time. This ancient radiation acts as a blueprint of everything that ever was and ever will be. When scientists mapped this relic radiation, they expected to find a completely random distribution of warm and cool patches scattered across the sky. After all, the universe has no center and no preferred direction. It should look the same no matter which way you turn your instruments. Yet, when we study the largest structures of this ancient map, we find a strange alignment. The warm and cool zones are not randomly scattered. Instead, they seem to line up along a specific axis. What makes this alignment truly bizarre is its orientation. This massive cosmic axis points directly along the plane of our own solar system. It is as if the entire universe, on its grandest scale, is aligned with the path our tiny Earth takes around the Sun. This unexpected pattern was given a dramatic name by physicists, the axis of evil, because it threatens to break our fundamental understanding of cosmology. We have long operated under the assumption that we do not occupy a special place in the universe. If the largest structures in the cosmos are somehow pointing at us, that assumption begins to crack. The universe should not have a preferred direction. Yet here, we find one that seems to whisper a story about our own backyard. Could this be a simple statistical fluke? Perhaps it is like flipping a coin and getting heads 20 times in a row. It is highly unlikely, but not impossible. Or maybe it is an error in our instruments. The dust within our own galaxy might be distorting the light, creating an illusion of alignment where none exists. Space telescopes have measured this light multiple times, and each time the alignment remains, challenging our calculations. If it is not an error, we may be uncovering a hint of a new cosmic geometry. Perhaps the universe is not the same in all directions. Maybe the cosmos has a shape we did not expect, like a giant torus, which forces light to travel in ways that create this alignment. Or perhaps there is a massive gravitational pull from something lying far beyond our horizon, tugging at the fabric of space. This could mean our understanding of gravity is incomplete. For now, the axis of evil remains one of the most quiet, unsettling mysteries of our sky. It invites us to contemplate our place in the cosmic dark, questioning if our local neighborhood is somehow connected to the grand architecture of the entire universe, or if we are simply misinterpreting the whispers of the ancient past. It leaves us with a quiet sense of wonder, reminding us how much of the cosmos remains beautifully unexplained. Tabbys Star. Imagine a porch light on a house miles away in the dark. Now imagine that light bulb flickering in a completely unpredictable way. Sometimes it dims slightly, almost imperceptibly. At other times it suddenly loses nearly a quarter of its brightness, dropping by 22%, before glowing brightly again. This is the mystery of a star located more than 1,000 light-years from our planet, known to astronomers as Tabbys Star. Under normal circumstances, when we search for worlds orbiting distant suns, we seek regular patterns. A planet passing in front of its star acts like a tiny clock. Every few weeks or months, it blocks a tiny fraction of the starlight, perhaps 1% or less. The dimming is always the same amount, and it happens on a strict schedule. This steady rhythm is how we identify new worlds. But this particular star does not follow the rules. Its light dips at random times, for different durations, and by massive amounts. A planet cannot cause this kind of behavior. If a planet were large enough to block 22% of a star's light, it would have to be giant, yet a giant planet would still pass by at regular, predictable intervals. Here, the shadows are chaotic. They appear without warning, linger for days, and then vanish. Scientists have proposed several ideas to explain these strange dips. One idea involves a massive swarm of cold comets, pulled in by a passing star, breaking apart and forming a messy, shifting cloud of debris. Another idea suggests a violent collision between two massive space rocks, or even a planet being ripped apart, leaving behind a thick ring of dust and rocky fragments. Some have suggested that the star might be swallowing a planet, causing it to release bursts of energy and light. Each theory attempts to explain the shadows, but each also raises new questions. Yet none of these explanations fit the data perfectly. Dust clouds should warm up and glow in infrared light, but observations have not detected the expected heat. For years, telescopes have recorded this flickering beacon, and the mystery has only deepened. Some dips last for days, others for weeks, and the shape of the dips is never the same. We are left with a puzzle that defies our current understanding of how stars behave. It reminds us that the cosmos is filled with objects that do not fit into our neat categories, leaving us to ponder the unknown in the quiet depth of the night. Fast radio bursts. Imagine sitting in a completely dark, silent sports stadium. Suddenly, a single camera flash goes off in a far corner, lasting for only 1,000th of a second, and then disappears. In that tiny fraction of a moment, that flash releases as much energy as our sun produces in an entire day. This is what astronomers experience when they detect a fast radio burst. These sudden, intense blasts of radio waves come from deep space, billions of light-years away, flashing briefly before vanishing into the quiet background of the cosmos. They are among the most energetic events in the universe, yet they remain deeply mysterious. We did not even know these bursts existed until 2007. A team of researchers was looking through old archived data collected by a giant radio telescope in Australia. They were searching for something else entirely, but instead, They found a massive, brief spike in the signals recorded years earlier. It was a single, powerful pulse that had traveled across the universe, undetected until someone decided to look closely at the old records. Since that first discovery, we have found many more of these cosmic flashes, and they have revealed a puzzling variety. Some of these signals are one-time events. They flash once, bright and brief, and never happen again, leaving us with no way to trace them back to their exact origin. Other signals repeat. They send out bursts multiple times, sometimes in a regular pattern, like a distant cosmic lighthouse sweeping its beam across the dark. This difference suggests we might be looking at two completely different kinds of events in the universe. So, what could be powerful enough to send a signal across billions of light years in the blink of an eye? One leading idea points to magnetars. These are dense remnants of dead stars with magnetic fields trillions of times stronger than the magnetic field of the Earth. A sudden crack in the crust of a magnetar, a star quake, could release a massive burst of energy. Another possibility is that we are witnessing cataclysmic collisions, such as two ultra-dense neutron stars colliding and merging into a black hole, releasing one final, powerful scream of radio waves before they disappear forever. We still do not have a single definitive answer. Each new flash we detect adds another piece to the puzzle, reminding us of how much remains hidden in the deep silence of space. Cosmic ray origin. Imagine a single tiny subatomic particle, far too small for any microscope to detect, traveling through the cold void of space. This particle is moving so fast, with such immense speed, that it carries the same amount of movement energy as a fast-pitched baseball thrown by a professional pitcher. If that baseball hit your hand, you would feel a solid, heavy thud. Now imagine all that force packed into a single proton, millions of billions of times smaller than a grain of sand. We call these fast-moving particles cosmic rays, and they rain down on our planet constantly from all directions. In 1991, scientists in Utah detected exactly such a particle. They named it the "Oh my God" particle because its energy seemed to defy explanation. It was traveling so close to the speed of light that if it raced a beam of light across the entire width of our galaxy, the light beam would only win by the tiniest fraction of a millimeter. Since then, we have detected more of these ultra-high-energy cosmic rays, yet their origin remains one of the greatest mysteries in modern astronomy. We simply do not know what kind of engine in the universe has the power to launch them. We struggle to find where they come from because of a cosmic game of misdirection. These particles carry an electric charge. As they travel across the universe, they must pass through vast magnetic fields that weave through galaxies and fill the space between them. These magnetic fields act like invisible hands, gently pushing and pulling on the charged particles, bending their paths into complex spirals and curves. By the time a cosmic ray reaches our atmosphere, it has been deflected so many times that it no longer points back to its source. The map of its journey has been completely erased. We look in the direction the particle came from, but we are looking at a detour, not the starting line. It is like trying to trace the path of a leaf carried by a turbulent river. For a long time, astronomers thought that supernovas, the violent explosions of dying massive stars, could be the source. These explosions are some of the most energetic events in the universe, sending shockwaves through space that can accelerate particles to extreme speeds. However, when scientists calculate the energy limits of a supernova, they realize these stellar explosions are simply not powerful enough to produce the most energetic cosmic rays. They lack the necessary strength to accelerate a particle to the extreme levels we observed in 1991. The magnetic fields within a supernova remnant cannot hold onto a particle long enough to boost it to such speeds. This leaves us searching for even grander cosmic engines. Perhaps they are born near the supermassive black holes at the centers of active galaxies, where intense magnetic fields spin like giant dynamos. Or maybe they are generated during the violent collisions of entire galaxies. As you rest tonight, these silent travelers continue to cross the vast emptiness, carrying secrets of distant, violent worlds we have yet to discover. Magnetic monopoles. If you hold a simple bar magnet in your hand, you feel its two opposite ends. One end points north and the other points south. It feels like a simple rule of nature. If you take a pair of cutters and snip that magnet right down the middle, you might expect to separate the north from the south. Instead, you end up with two smaller magnets. Each one instantly develops its own north and south pole. You can repeat this process, cutting the pieces smaller and smaller, even down to individual atoms. Every single piece remains a double-sided magnet. In our everyday experience, magnetic poles always come in pairs. Yet, the deep mathematics of physics tells us a different story. When we look at the equations that describe the quantum world, they suggest a strange possibility. Grand unified theories, which attempt to unite the forces of nature, predict the existence of a particle with only one magnetic pole. A magnet that is only north or only south. These theoretical particles are called magnetic monopoles. They are predicted to be extremely heavy, perhaps as heavy as a tiny bacterium, concentrated into a space smaller than an atom. Physicists have searched for these elusive particles for decades. On a quiet night in February of 1982, a physicist named Blas Cabrera set up an experiment. He used a coil of superconducting wire designed to detect the unique signature of a single magnetic pole passing through it. At 2 o'clock in the morning, the instrument recorded a signal. It was a perfect match for a magnetic monopole. The event caused a wave of excitement, but the experiment was never able to replicate the result. The single detection remains a mystery, a solitary whisper in the dark that left scientists holding a question mark. The absence of these monopoles presents a profound puzzle. If they were created during the high-energy birth of the universe, we should see them today. Their complete absence supports a theory about our cosmic origins. It suggests that a fraction of a second after the beginning of time, the universe underwent a rapid, unimaginable expansion. This expansion stretched space so quickly and so vast that any magnetic monopoles created were scattered across the cosmos. They became so spread out that we might live in a region of space where we will never encounter one. We are left holding our two-sided magnets, contemplating a universe that keeps its deepest secrets hidden in the vastness of space. The fate of the universe. Let us think about how a story ends when the rules of gravity and the unseen pressure stretching our space are still being written. We live in a cosmos that is growing larger every single second. But will this growth continue forever, or is there a final page to the book of reality? Scientists often speak of three possible endings for everything that exists. The first path is a slow drift into quietness, often called the Big Freeze. We can think of a house where the fireplace slowly burns down, and no one is there to add more wood. Over trillions of years, stars will consume their fuel and fade into embers. Galaxies will drift too far apart to interact. The sky will grow darker as the light from distant places can no longer reach us. Eventually, even the smallest particles will wander alone in a cold, silent void, so far from each other that they can never meet or share warmth again. The second path is much more sudden and violent, known as the Big Rip. In this scenario, the unseen force pushing the universe apart grows stronger and stronger. It begins by pulling galaxies away from each other, but it does not stop there. The push becomes so intense that it tears solar systems apart, separates planets from their stars, and eventually rips solid rocks, molecules, and even atoms into pieces. In the end, the very fabric of space itself is shredded, leaving nothing behind. The third path is a complete reversal, called the Big Crunch. This is the idea that gravity might eventually win the tug of war. If the gravitational pull of all the matter in the cosmos is strong enough, it could slow down the expansion and eventually stop it. The universe would then begin to fall inward, contracting like a balloon losing its air. Galaxies would merge, and the temperature of space would rise. In the final moments, everything we have ever known would be squeezed back into a single, infinitely hot and dense point, perhaps preparing for another great beginning. Which of these endings awaits us depends entirely on a delicate balance. It is a competition between the pulling force of gravity and the outward push of cosmic expansion. We do not yet know the exact strength of these forces over long periods of time. A tiny shift in the balance could mean the difference between a silent, frozen infinity and a sudden collapse. As we lie here in the quiet of the night, it is strange to contemplate a future where all the stars have gone out. The atoms that make up our bodies, our world, and our memories may one day drift in an endless, quiet dark, or return to the hot furnace where everything began. It reminds us how precious and brief this bright, warm moment in the history of the cosmos truly is. Quantum gravity. Imagine playing a game where the rules change completely depending on the size of the board. If the board is large, you follow one set of laws. If you shrink the board down to a microscopic scale, those laws no longer work, and a completely different set of instructions takes over. This is the quiet crisis at the very heart of modern physics. Our understanding of the universe is built on two separate, highly successful rulebooks that seem to flatly contradict each other. On one side, we have the theory of Albert Einstein, known as general relativity. It is a beautiful, elegant description of the cosmos on a grand scale. It paints a picture of space-time as a smooth, continuous fabric. Massive objects like stars and planets warp this fabric, and we experience that warping as gravity. It is predictable, orderly, and smooth. If you know where a planet is today, you can calculate exactly where it will be in 1,000 years. On the other side, we have quantum mechanics, which governs the subatomic world. Here, the smooth fabric of space-time is replaced by a chaotic, choppy arena. In this microscopic realm, particles do not have definite positions. Instead, they exist in a cloud of probabilities, constantly buzzing, shifting, and popping into and out of existence. It is a world of uncertainty and sudden jumps. For nearly 100 years, physicists have tried to merge these two worlds into a single framework called quantum gravity. The difficulty lies in the nature of gravity itself. We have successfully applied quantum rules to the other forces of nature, like electromagnetism. We can think of the electromagnetic force as being carried by tiny, discrete packets of energy. But when we try to do the same with gravity, the mathematics breaks down. If we try to calculate the gravitational interaction between two particles at extremely close range using quantum math, the equations yield infinite results. In physics, an answer of infinity usually means the theory is missing something vital. To bridge this gap, scientists have proposed several ideas, though none are proven. One major approach is string theory, which suggests that the fundamental building blocks of nature are not point-like particles, but tiny, vibrating strings of energy. Different vibrations create different particles, including the hypothetical carrier of gravity. Another idea is loop quantum gravity, which proposes that space-time itself is not a smooth sheet, but is woven out of tiny, discrete loops. In this view, space has pixel-like properties, and you cannot have a distance smaller than a certain fundamental limit. We need a working theory of quantum gravity to explain what happens in the most extreme environments in the cosmos, such as the very birth of our universe, or the ultimate center of a collapsed star. Without it, our equations lead to mathematical breakdowns that we cannot resolve. Until we find a way to unite the physics of the very large with the physics of the very small, our picture of reality remains divided, waiting for a deeper truth to tie it all together. Stellar age discrepancy. Imagine walking into a room and meeting a child who is older than the parent who gave them birth. It sounds like a logical puzzle, or perhaps a simple mistake on a birth certificate. Yet, when we turn our telescopes toward the deep cosmic suburbs of our own galaxy, we find a single star that seems to tell this exact impossible story. It challenges our basic understanding of time and cosmic history. This star is known to astronomers by a rather dry catalogue name, HD 140,283. Because of its extreme age, researchers have given it a far more poetic title. We call it the Methuselah Star. It sits about 200 light-years away, rushing through our stellar neighborhood at a tremendous speed. For decades, this ancient wanderer has kept astronomers awake at night, raising questions that we still struggle to resolve. When scientists first calculated the age of this star, they looked at its brightness, its temperature, and the specific chemical elements it contains. The calculations returned a result that did not make sense. The math suggested the star was over 14 billion years old. This created a profound problem. According to our best measurements, the universe itself is only 13.8 billion years old. A star cannot exist before the universe does. You cannot hang a painting without a wall to support it. To solve this mystery, astronomers worked for years to refine their measurements. They gathered more precise data on the distance of the star, which helped them determine its true brightness. They updated their models of how stars burn through their fuel, and they carefully analyzed the chemical composition of its core. They also accounted for the natural margins of error in their instruments. These new calculations brought the estimated age down, placing it at around 14.5 billion years, and then closer to 13.7 billion years when accounting for all uncertainties. This adjustment technically allows the star to fit within the lifetime of the universe, but only by the thinnest of margins. The two numbers are still uncomfortably close, leaving very little room for error. The tension in our stellar evolutionary models remains. We are left with a lingering question about how well we understand the life cycle of stars, and how we measure the age of the cosmos itself. The Methuselah Star remains a quiet, glowing reminder that our cosmic timelines might still need some rewriting, and that the universe is under no obligation to make its history simple for us to read. Lithopanspermia. Imagine a quiet piece of rock drifting slowly through the dark, cold vacuum of the cosmos. It is a tiny, silent fragment broken off from an ancient, forgotten world, perhaps billions of years ago. Inside the microscopic, frozen cracks of this stone, small microbes lie completely still, wrapped in a deep, dreamless sleep. They are waiting, protected from the harsh, destructive rays of distant stars, traveling quietly through the silent dark. This is the core idea of lithopanspermia, the intriguing theory that life might travel between different planets, riding on pieces of cosmic debris like silent biological passengers on a natural spaceship. For a very long time, scientists believed that the cold vacuum of space was completely hostile and lethal to any living thing. Yet, we have discovered organisms on our own planet that challenge this assumption in surprising ways. Microscopic creatures like tardigrades, which are often called water bears, can survive the most extreme conditions imaginable. When researchers expose them to the freezing cold of space, the absolute lack of air, and the intense radiation, they do not die. Instead, they enter a special state of suspended animation, drying out completely and turning off their metabolism. They simply wait for conditions to improve. If these tiny, resilient creatures can survive on the cold outside of our spacecraft, it makes us wonder if they could survive a long journey lasting millions of years inside a deep space rock. The journey of such a rock begins with a violent cosmic collision. When a massive asteroid strikes the surface of a planet with immense speed, the incredible force of the impact can launch surface rocks directly into space, sending them past the gravity of their homeworld. We know this process actually happens because scientists have found pieces of Martian rock right here on Earth. These ancient meteorites survived the immense shock of the initial impact, the long journey through the void of space, and the fiery heat of falling through our atmosphere. If those rocks carried tough microbes deep within their cracks, those microscopic organisms could have survived the entire trip. This raises a profound and beautiful question. What if the story of life did not start on Earth at all? Perhaps, long ago, a traveling rock from a distant, unknown solar system drifted slowly into our path. It could have carried the microscopic ancestors of all living things today, seeding our warm young oceans with the first sparks of biological life. We are constantly searching for answers, but for now, we do not know if life can truly bridge the vast, lonely distances between the stars. The universe remains completely silent on this matter, keeping the secret of our true origin locked away in the quiet drift of cosmic stone. The boundary of the universe. Imagine you are floating in a vessel capable of traveling at speed through the cosmic dark. You choose a direction, point your ship forward, and travel in a straight line forever. You never slow down, and you never steer. Perhaps you expect to eventually reach a wall, a physical barrier marking the edge of everything. Instead, you continue on and on, only to find yourself eventually drifting back to the exact spot where your journey began. You did not turn around, and yet the loop is complete. This thought experiment is one of the ways cosmologists try to conceptualize the shape of our universe. To understand this, we have to consider the difference between what we can observe and what actually exists. The observable universe is a sphere centered on us, spanning about 93 billion light-years across. This boundary is set by the speed of light and the age of the cosmos. It is simply the limit of how far light has traveled to reach us since the beginning of time. But beyond this horizon lies the rest of the universe, an unseen expanse that could extend infinitely, or perhaps fold back on itself in ways that challenge our daily intuition. For a long time, scientists have tried to measure the curvature of space to determine if it is open, closed, or flat. Data gathered by the Planck satellite suggests that, as far as we can measure, the geometry of our universe is flat to a very high degree of precision. In a flat universe, parallel lines never meet, and triangles always have angles that add up to exactly 180 degrees. On a curved surface, like a giant ball, those rules change, and lines eventually cross. If the universe is flat, it seems logical to assume it must go on forever, without end. However, a flat universe does not have to be infinite. It could be finite through its topology. Think of the classic early video games. When your character moves off the right side of the screen, they instantly reappear on the left side. The screen has no physical border, no edge where the game stops, yet the space itself is limited. The screen is wrapped. We can imagine this like a piece of paper rolled into a tube, or even a donut shape, where every direction connects back to its origin. In 3 dimensions, our universe could share a similar structure. Space could be flat, yet folded in on itself in a way that connects opposite sides. If you travel far enough in one direction, you simply loop back. We are left with a profound mystery. We cannot see far enough to know if the universe goes on forever, or if it is a giant, repeating cosmic hall of mirrors. If space has no physical edge, What about the dark objects that might have formed before the first stars even lit up? Primordial black holes, awaiting task code. Strange stars. Consider a star that has died and collapsed, leaving behind an object so dense that it defies comprehension. It is a stellar remnant so compact that a single teaspoon of its material would weigh as much as a mountain, perhaps 900 billion kilograms. This is a neutron star, which is essentially a giant atomic nucleus the size of a city, packed with the mass of a sun. Usually, atoms are mostly empty space. But inside a neutron star, gravity has crushed the electrons and protons together, forcing them to become neutrons. These neutrons are packed together as tightly as physically possible, leaving no empty space at all. Yet, there is a theory that at the very center of these dead stars, where the weight of the entire stellar remnant presses down, the pressure becomes so extreme that even the neutrons themselves begin to dissolve. Normally, neutrons are made of smaller particles called quarks, specifically up quarks and down quarks, which are bound tightly together. But under the unimaginable weight of a collapsing star, the boundaries between individual neutrons might melt away. The result is a hot, dense soup of free-floating quarks. Scientists suggest that some of these quarks might transform into a heavier type of quark, known as a strange quark. If this happens, it creates a new phase of matter called strange quark matter. This is a unique state of matter, a substance that could behave in ways that are deeply unsettling. Some physicists propose that strange matter might actually be the most stable form of matter in the entire universe. Normal matter, the stuff that makes up your body, the Earth, and the Sun, is stable because of the laws of physics we observe daily. However, it is possible that normal matter is actually in a temporary state, and that strange matter represents a lower, more permanent energy level. If this idea is correct, it leads to a strange and terrifying concept. If a piece of strange matter were to escape its star and travel through space, it would be highly contagious. Because it is more stable than normal matter, any ordinary atom it touches would immediately want to slide into this lower energy state. The moment a tiny droplet of strange matter, called a strangelet, touches normal matter, that normal matter would instantly dissolve and convert into strange matter. A single stray strangelet landing on Earth could initiate a chain reaction, silently and rapidly transforming our entire planet, the oceans, the atmosphere, and every living thing into a single dense sphere of strange matter. We do not know if these strange stars exist. They would appear almost identical to regular neutron stars from the outside, hiding their alien cores deep within. They remain one of the most intriguing and slightly haunting possibilities in the cosmos, a reminder that the fundamental rules of reality might change under pressure. The cool spot. Imagine looking at a vast baby picture of our universe, a map of the very first light that escaped into the darkness billions of years ago. For the most part, this ancient light is almost perfectly even. It spreads across the sky with tiny, gentle variations in temperature, like the ripples on the surface of a quiet pond. But in one particular patch of the southern sky, there is a giant, freezing shadow. Scientists call it the cold spot. It is an enormous region that is significantly colder than everything around it, and by all the laws of cosmic history, it simply should not exist. To understand why this cold patch is such a puzzle, we have to think about how large it is. This is not a small pocket of space. It stretches across nearly 1.8 billion light-years. If you could travel at the speed of light, it would take you almost 2 billion years to cross this single frigid zone. Our current understanding of the early universe suggests that energy and matter should have spread out quite evenly. Small differences are normal, but a cold patch of this size is highly improbable. It is like finding a massive block of ice floating in the middle of a warm bath. One theory to explain this mystery is the existence of a supervoid. Imagine a cosmic desert, a region of space containing far fewer galaxies and stars than the rest of the universe. When light travels through space, it falls into the gravitational wells of galaxies, gaining energy, and then climbs back out, losing energy. If the universe is expanding while the light is traveling, the light loses a little more energy climbing out of a void than it gained entering it. A massive supervoid could drain enough energy from the passing light to make that region look cold to our detectors. Yet, even the largest supervoids we can imagine do not seem large enough to fully explain this temperature drop. The math does not quite add up. This leaves us with more radical possibilities. Some scientists suggest that the cold spot might be a physical bruise on the fabric of our space. They propose that our universe is only one of many, floating like bubbles in a grand multiverse. In this view, our bubble universe may have bumped into another neighboring universe long ago, leaving a permanent scar in the cosmic light. It is a mind-bending thought. The coldness we observe could be the direct footprint of a completely different reality touching our own. Whether it is an impossibly large cosmic desert or a signpost for other universes, the cold spot remains an open question. It stands as a silent reminder that our maps of the cosmos are still incomplete, and that the darkness of space still holds secrets far larger than we can imagine. The first stars. Imagine traveling back in time, far beyond the birth of our solar system, past the formation of the first recognizable galaxies. We arrive at a period about 100 million years after the Big Bang. The universe is a vast, silent ocean of dark hydrogen and helium gas. There are no stars, no planets, and no light. This era is known to astronomers as the Cosmic Dark Ages. In this absolute blackness, gravity is slowly, patiently pulling giant clouds of gas together. It is a slow, quiet process, taking millions of years to draw enough material together to spark the first flame. These pristine clouds contain only the simplest elements. Unlike the gas clouds that exist today, which are rich with carbon, oxygen, and iron, these early clouds are perfectly clean. This lack of heavy elements changes everything. Heavy elements help modern gas clouds cool down and break into smaller pieces to form small stars like our Sun. Without them, the ancient clouds cannot easily cool. They have to grow enormous, gathering massive amounts of material before they can finally collapse and ignite. As a result, the very first generation of stars had to be giants, born from necessity in a much larger way than stars are born today. When they finally light up, they form the very first stars, which scientists call population 3 stars. These giants are unlike anything in our modern night sky. They are monsters of pure hydrogen and helium, perhaps 30 to several hundred times more massive than our Sun. They burn with a fierce, brilliant blue light, burning hot and intensely bright. Because they are so massive, they burn through their nuclear fuel at a rapid pace. While a star like our Sun can live for 10 billion years, these first giants live for only a few million years before dying in massive supernova explosions. We have never actually seen one of these first stars. Their light is extremely faint by the time it reaches us, stretched by the expansion of space into long, invisible infrared wavelengths. Even our most powerful space telescopes struggle to find them. Astronomers search for their faint glow or the chemical fingerprints they left behind in the second generation of stars. Finding them would be like finding the first page of the cosmic diary, telling us how the dark universe first woke up and began its long journey toward the star-filled sky that shines tonight. Until then, these first stars remain hidden in the deep shadows of the ancient past, a beautiful mystery waiting to be solved. a hidden outer planet. If you travel far past the cold orbit of Neptune, out into the frozen, quiet edges of our solar system, you enter a vast ring of icy debris known as the Kuiper Belt. In this dark region, trillions of small, frozen objects drift in the silence of space, far from the warmth of the sun. For a long time, we thought we understood this quiet neighborhood, believing it to be a lonely graveyard of ancient ice. But in recent years, astronomers noticed something strange. A small group of these distant icy bodies, traveling on giant paths around the sun, are all tilting and clustering in the exact same direction. Imagine walking into a dark room and seeing a dozen spinning tops, all leaning at the exact same angle, pointing toward the same corner. You would naturally think some unseen force, like a gentle breeze or a slope in the floor, was causing them to tilt. In the quiet dark of the outer solar system, gravity is the force tilting these icy worlds. The paths they take are so synchronized that the chance of this happening by pure accident is less than 1 in 10,000. This suggests that a massive hidden neighbor is pulling on them with its gravity, gently guiding their long journeys through the dark. Calculations suggest this invisible world is huge, perhaps 5 to 10 times the mass of our own Earth. If it exists, it would be a true giant, orbiting the Sun at a distance so great that a single year on this planet would last between 10,000 and 20,000 Earth years. This means that while our own planet has completed thousands of journeys around the Sun, this silent neighbor has not even finished one. Finding it, however, is one of the greatest challenges in modern astronomy. At such an immense distance, the Sun is nothing more than an exceptionally bright star in the sky. This distant world receives almost no sunlight, and it reflects even less back to us. It is a cold, dark sphere, sliding silently against a background of billions of distant twinkling stars. Searching for it is like trying to spot a single black marble lost on a vast, dark, sandy beach using only a tiny flashlight. We must scan tiny patches of the sky, night after night, hoping to catch the slightest movement against the background stars. Until we capture that faint glimmer of reflected light, this giant world remains a ghost, a silent shadow reshaping our cosmic neighborhood from the deep freeze of space. We are left looking at the ripples in the pond, waiting to see the stone that made them. The solar corona heat. Let us step close to a campfire. You feel the intense heat radiating from the glowing wood. As you walk away from the embers, the air quickly cools down. This makes intuitive sense. The further you go from a heat source, the colder it gets. Yet, if we consider our own sun, this basic rule of nature seems to break down completely. This puzzle has kept researchers searching for answers for decades. The surface of the sun, called the photosphere, sits at about 6,000 degrees. This is hot enough to melt any material we have on Earth. But as we move outward, away from this blazing surface, and into the outer atmosphere, known as the corona, the temperature does not drop. Instead, it rises dramatically. The corona reaches temperatures between 1 million and 3 million degrees. It is as if you walked a mile away from a campfire and suddenly found yourself standing in air that is hundreds of times hotter than the fire itself. It contradicts our daily experiences with heat and energy transfer. How does this happen? For decades, astrophysicists have struggled to find a clear answer. One leading idea involves the magnetic fields of the sun. The surface of the sun is a churning ocean of charged particles, which twist and stretch magnetic field lines. When these lines become too tangled, they can snap and reconnect, releasing massive bursts of energy. Some scientists believe that millions of tiny explosions, called nanoflares, are constantly erupting all over the sun. These tiny bursts might be sending waves of energy upward, heating the thin gas of the corona to these extreme temperatures. Even though we have sent spacecraft to study this mystery directly, a definitive answer remains out of reach. The Parker Solar Probe has flown directly through the outer atmosphere of the Sun, tasting the hot plasma and measuring the magnetic fields. These missions have gathered invaluable data, but they have also revealed an environment that is far more complex than we anticipated. The exact mechanism that carries the heat upward remains a subject of intense debate. We are left with a star that defies our simple expectations, reminding us that even the most familiar objects in our sky still hold secrets we cannot yet fully explain. Perhaps the answer lies in the subtle dance of magnetic fields that we are only beginning to comprehend. Fast stellar velocities. Imagine a lone star, bright and massive, hurtling through the deep darkness of space at more than 2 million miles per hour. It is moving so fast that the gravitational pull of our entire galaxy cannot hold it back. This star is on a one-way journey, escaping the Milky Way forever to drift in the empty void between galaxies. Astronomers call these fast-moving wanderers hypervelocity stars. For a long time, we thought we understood how a star could get such a tremendous kick. The explanation points to the giant black hole at the very center of our galaxy. Imagine a pair of binary stars orbiting close to each other, dancing through the crowded galactic core. If this pair passes too close to the supermassive black hole, the intense gravity can tear them apart. The black hole captures one star, pulling it into a tight, permanent orbit. The other star, suddenly freed and boosted by the gravity of the giant, is flung outward at an extreme speed, like a stone released from a cosmic slingshot. It is a violent breakup that sends one partner flying into exile. Yet, this explanation does not solve the entire mystery. When scientists tracked the paths of some fast-moving stars, they found something unexpected. Many of these speedsters do not trace back to the center of the galaxy. Instead, they seem to originate from the outer disk, far from the central black hole. How did they get their speed? One possibility is a supernova explosion. If a star is orbiting close to a companion that explodes, the sudden loss of mass can release the surviving star like a cut rope, sending it sailing away. Another theory suggests these stars might be leftovers from a collision with a smaller dwarf galaxy that our Milky Way absorbed long ago. Or perhaps there are medium-sized black holes hiding in the outer parts of the galaxy, quietly throwing stars out into the dark. Whatever their origin, these stars face a lonely destiny. Once they escape the gravity of the Milky Way, they enter the intergalactic void. This is a vast, cold expanse where the distance between galaxies is measured in millions of light years. As the millions of years pass, the star will continue to shine, burning through its nuclear fuel all alone in the deep dark. If planets orbit such a star, the night sky for any observer there would slowly fade to complete blackness, as the familiar band of the Milky Way shrinks into a tiny, distant smudge of light. They would be left in a universe without neighboring stars, drifting forever in the quiet, empty night. Void space. Let us begin by imagining the universe on the grandest scale. It resembles a vast cosmic spiderweb where the delicate, glowing threads are made of light and billions of galaxies. These bright filaments stretch across the dark, wrapping around giant spheres of absolute nothingness. These empty spaces are called cosmic voids, and they are the quietest, most isolated places in existence. They are the blank canvases of the cosmos, stretching across distances that challenge our ability to comprehend size. In this scale, galaxies are just tiny dust motes, clinging to the edges of vast hollow caverns. One of the largest known gaps is the Boots Void, a region of space so immense that it makes our own galaxy look like a tiny grain of sand. It spans nearly 330 million light-years across. To understand its scale, we can compare it to our own cosmic neighborhood. If the Milky Way galaxy were located in the center of the Boots void, we would have felt completely alone. We would not have known that other galaxies existed until the middle of the 20th century, because the nearest neighboring star systems would have been too distant for our early telescopes to detect. It is a desert of darkness, containing only a tiny handful of lonely galaxies scattered through its vast, quiet interior. A traveler crossing this void would see only blackness in every direction for millions of years. These quiet spaces grow larger over time through the simple physics of gravity. In the early universe, matter was distributed almost evenly, but some regions had slightly more material than others. Gravity slowly pulled gas, dust, and stars toward these denser areas. As the dense filaments grew stronger, they dragged matter away from the emptier regions. Over billions of years, the voids were drained of their substance, becoming emptier and emptier as the surrounding walls of galaxies grew thicker. It is a cosmic game of tug-of-war where the dense regions always win, pulling the contents of the universe toward themselves. Yet, our calculations show that these voids are far emptier than our models of cosmic structure formation predict. There are far fewer stray atoms and particles in these cold expanses than our theories suggest should be left behind. This extreme emptiness raises deep questions about the forces shaping our universe. We know that dark energy plays a role in driving the expansion of these voids, pushing their boundaries outward and stretching the empty space. But the sheer lack of normal matter inside them suggests we do not fully understand how gravity and expansion interact on the largest scales. These silent gulfs remain a mystery, reminding us that the gaps between the stars hold secrets just as deep as the stars themselves. We contemplate the darkness and realize that the emptiness has its own story to tell. Alien biosignatures. Imagine a tiny pinprick of starlight that has traveled through the cold void of the cosmos for trillions of miles. As this light passes through the thin blanket of air surrounding a distant alien world, it carries away a secret code. By stretching this starlight into a rainbow, scientists detect dark lines where specific gases have swallowed certain colors. When a planet crosses directly in front of its host star, a tiny fraction of starlight skims through the thin ring of its atmosphere. The gas molecules there absorb specific wavelengths, leaving these telltale dark bands in the light that finally reaches our telescopes. This is how we search for the breath of a living planet from across the vast ocean of space. We look for gases that on our own homeworld are closely tied to the presence of living things, such as oxygen, methane, or a strange gas called phosphine. On Earth, oxygen is constantly pumped into the sky by forests and tiny ocean plants, while methane is released by billions of microbes. When we detect these chemicals in the light of a faraway star, we feel a sudden spark of hope, as if we are catching a quiet whisper of life from the deep dark. Yet, this whisper is often a trick of chemistry. Every gas we associate with life can also be brewed in the quiet, violent kitchens of dead planets. Methane can leak from deep volcanic vents or form when water reacts with hot minerals deep underground. Oxygen can accumulate on a dry, lifeless world when harsh, ultraviolet light breaks apart water vapor in the upper atmosphere, letting the light hydrogen escape into space while leaving the heavy oxygen behind. Even phosphine can be forged under the immense heat and pressure of deep gas giant atmospheres. When we study a spectral fingerprint from many light years away, we cannot easily tell if we are observing the metabolism of billions of tiny cells, or simply the slow, rhythmic exhaling of ancient volcanoes. This is the great challenge of searching for life on worlds we cannot touch. We are forced to study a planet as a single, faint point of light, trying to reconstruct an entire global ecosystem from a chemical glow. To be absolutely sure we have found life, we must understand the entire world as a single working system. We have to map its geological activity, trace the intense light of its parent star, and model the chemistry of its oceans. Without physically visiting these places, sending robotic probes that would take thousands of years to arrive, we may never reach a final, certain answer. We are left studying these distant chemical signatures, forever wondering whether we are hearing the heartbeat of an alien biosphere, or simply the cold, beautiful, and lonely song of chemistry. The fine-tuning of constants. Suppose we stand in front of a massive control console that governs the entire cosmos. On this board are dozens of dials, each representing a fundamental constant of nature. One dial sets the strength of gravity. One dial sets the strength of gravity. Another controls the mass of an electron. A third determines the power of the force that holds atomic nuclei together. Upon closer inspection of these dials, we notice something strange. Every single one of them is set to the exact value necessary for complexity to exist. If you were to nudge almost any dial by even the hair of a millimeter, the universe we know would vanish. Why are the knobs of physics turned to the exact values that allow atoms, stars, and people to exist? Let us begin with the force of gravity, the gentle pull that holds us to the ground and keeps the planets in their orbits. Gravity is the weakest of the four forces, yet it shapes the largest structures in the cosmos. If gravity were even slightly stronger, stars would be far more compressed. They would burn through their fuel at a furious pace, collapsing into black holes long before life could ever find a foothold on any planet. If gravity were a fraction weaker, matter would never gather together in the first place. The universe would remain a cold, diffuse gas with no stars, no planets, and no warm suns to light the dark. We find the same delicate balance in the strong nuclear force, the glue that binds protons and neutrons inside the hearts of atoms. If this force were only a tiny bit weaker, hydrogen would be the only element in existence. Heavier atoms could not hold themselves together, meaning we would have no carbon, no oxygen, and no chemistry. The cosmos would be sterile. If this force was slightly stronger, all the hydrogen in the early universe would have fused into helium during the opening moments of creation. This would leave no hydrogen to fuel the long-burning stars, and no hydrogen to form water. Even the tiny mass of the electron is dialed in with extreme precision. If the electron were heavier or lighter, chemical bonds would fail to form. The molecules that build our cells, the water we drink, and the air we breathe would simply fall apart. This extreme precision leaves us with a profound puzzle. Some scientists point to the anthropic principle. This idea suggests that we observe a finely tuned universe simply because we could not exist to ask the question in any other kind of world. If the dials were set differently, no one would be here to wonder about them. It is a simple explanation, but it leaves many feeling unsatisfied. Others hope for a deeper, hidden law of nature, a grand unifying theory that explains why these constants must be exactly what they are. In this view, the dials are locked in place by some underlying rule we have yet to discover. We are caught in a tension between these two paths, searching for meaning in the numbers that define our existence. But what if our universe is not the only setting on the dial? Multiverse Hypothesis. Imagine a vast ocean of boiling water. As the water heats up, bubbles form, expand, and rise. Now, let us imagine that each of these bubbles is not filled with steam, but is instead an entire self-contained universe. Within one bubble, the laws of physics might allow stars and planets to form, just like our own. In the bubble next to it, the rules could be entirely different, perhaps with gravity so strong that everything collapses back into a point, or so weak that atoms can never join together. We might find ourselves in a universe that is perfectly suited for life, while a neighbor bubble remains cold, empty, and dark, devoid of any structure at all. This is the picture painted by the idea of eternal inflation. We often think of the rapid expansion at the beginning of our universe as a one-time event, but some theories suggest that this expansion never truly stops everywhere. Instead, it is an ongoing process that happens forever across a wider cosmos. In most places, space keeps stretching at a speed faster than light. But occasionally, in small pockets, the expansion slows down. These pockets settle, cooling into quiet zones. Each quiet zone becomes a bubble universe, isolated and drifting in a vast, ever-growing sea of expanding space. Our own home, with all its galaxies, stars, and history, would be just one of these tiny bubbles. The challenge we face is that we are locked inside our own bubble. The space between the bubbles is expanding so rapidly that no light, no signal, and no traveler could ever cross the gap. We are bounded by our cosmic horizon, which is the absolute limit of how far light has been able to travel to reach us since our beginning. Anything beyond that horizon is forever out of our reach. We cannot peer through the edge of our bubble to see if another one is floating nearby. There are no experiments we can run and no telescopes we can build that could gather data from outside our own universe. We are, in a very real sense, trapped in a bubble of our own history, unable to verify the existence of anything beyond. This brings us to a deep and unsettling question about the nature of science itself. If a theory predicts something that we can never observe, test, or disprove, does it still belong to the realm of science? For generations, the foundation of scientific inquiry has been the ability to test our ideas against reality. When we propose a universe that exists beyond any possible observation, we cross a line from physics into philosophy. Some argue that if the math points to a multiverse, we must accept it as a possibility. Others believe that without the ability to gather evidence, we are simply telling stories. We are left to contemplate whether we are truly alone in a single, solitary universe, or if we are merely one quiet note in an infinite, unreachable symphony. Galaxy rotation curves. A playground merry-go-round spins under the warm afternoon sun. If you stand near the center, holding onto the metal bars, you feel a gentle tug. If you step to the very outer edge, the spin feels much faster, and you have to hold on tight to avoid being thrown off into the grass. In our solar system, gravity works in a similar way. The inner planets, like Mercury, zip around the sun at high speeds. The outer planets, like Neptune, creep along slowly because the gravitational pull of the sun weakens with distance. This is how Isaac Newton explained the cosmos, and for centuries, this rule held true. It seemed to govern every spinning object in the night sky. But in the 1970s, an astronomer named Vera Rubin turned her telescope toward distant spiral galaxies to measure how fast their stars were rotating. She expected to see the outer stars moving much slower than the inner stars, just like the outer planets in our solar system. Instead, she found something that challenged our understanding of physics. The stars at the very edges of these galaxies were traveling at the exact same speed as the stars near the center. It was as if the merry-go-round was spinning, and the riders on the very edge were moving just as fast as the riders near the middle, yet they were not flying off into the void. By all the rules of gravity we understood, these outer stars should have been flung out into deep space. The visible mass of the galaxy, the stars and gas clouds we can see, simply did not have enough gravitational pull to keep them held in their orbits. They should have drifted away, leaving the galaxy to unravel. To explain this mystery, scientists proposed two very different ideas. The first idea is that there is a vast, invisible halo of unseen mass surrounding each galaxy. This hidden mass provides the extra gravitational grip needed to hold the outer stars in place. It is a massive, silent scaffolding that we cannot see, yet it dictates the movements of everything we do see. The second idea takes a different path. Instead of adding invisible mass, it suggests that our understanding of gravity is incomplete. This concept, known as modified Newtonian dynamics, proposes that at very low accelerations, such as those experienced by stars at the edges of galaxies, gravity behaves differently than it does here on Earth. In these outer regions, gravity does not weaken as quickly as Newton predicted. Both ideas attempt to solve the same puzzle. One introduces an invisible source of gravity, while the other rewrites the laws of gravity themselves. Decades after the initial observations, we still do not have a definitive answer. The debate remains open, and the cosmos continues to keep its secrets. The outer stars continue their swift, silent orbits, holding on to mysteries that challenge our view of the universe. Wormholes. Imagine holding a simple sheet of paper. On one side, you draw a small black dot. On the opposite side, far away, you draw another. Normally, to travel from one dot to the other, you must move across the entire length of the page. But what if you fold the paper in half, so that the two dots lie directly on top of each other? If you poke a pencil straight through both layers, you create a shortcut. You have connected two distant points through a gap in space. This is the classic way we try to conceptualize a wormhole. In the language of physics, this shortcut is known as an Einstein-Rosen bridge. Albert Einstein and Nathan Rosen realized that the equations of general relativity allow for these tunnels through the fabric of the universe. In theory, gravity can bend space and time so intensely that it creates a portal connecting two vastly separated locations, or perhaps even two different times. It is as if the universe contains secret back doors that bypass the cosmic speed limit of light. If you traveled through one, you could cross millions of light years in a fraction of a second, moving across the cosmos faster than any rocket could ever dream of. But there is a catch. The mathematics that allows a wormhole to exist also suggests it would be extremely unstable. The moment even a single particle of light tries to pass through, the tunnel would pinch shut, collapsing into a black hole before anything could cross. To keep this throat open, we would need something extraordinary. We would need a substance known as exotic matter, which possesses negative energy density. This is not normal matter, nor is it antimatter. It is a hypothetical substance that acts with a repulsive gravitational force, pushing the walls of the tunnel outward against the crushing weight of gravity. We do not know if such matter actually exists in our universe, or if it is just a mathematical placeholder. Even if we could find this exotic matter and build a stable doorway, we would face deep questions about causality. A traversable wormhole could potentially link two places in space and also connect 2 points in time. If you were to step through, you could arrive at your destination before you even departed. This opens the door to paradoxes where an effect could precede its cause, threatening to unravel the logical consistency of our reality. Would the universe allow such shortcuts, or does some undiscovered law of physics prevent them from forming in the first place? We are left gazing at the mathematics, wondering if these cosmic tunnels are real pathways through the dark, or merely beautiful mirages written on the blackboard of science. White holes. Imagine a door that only opens outwards. You can stand on the threshold and watch things emerge from it, but no matter how hard you push, you can never step inside. In the strange language of physics, this is the concept of a white hole. We are familiar with black holes, those cosmic traps where gravity is so strong that nothing, not even light, can escape once it crosses the border. A white hole is the exact opposite. It is a region of space that constantly spits out matter and energy, acting like a cosmic fountain, while refusing to let anything enter. If you tried to fly a spaceship into a white hole, the force of the outgoing energy would push you back, making it impossible to ever reach the center. It is a place that exists only to give, never to take. This strange concept comes directly from the mathematical equations of general relativity, the very same framework that predicted black holes. Albert Einstein wrote down these equations to describe how gravity bends the fabric of space and time. When physicists analyzed his math, they realized the equations do not care about the direction of time. They work just as well in reverse. If you run a video of a collapsing black hole backward, you get a white hole. In theory, they are two sides of the same coin, equally valid under the laws of physics. Yet, while we have confirmed the existence of black holes across the universe, we have never detected a single white hole. Why is that? One explanation lies in the fundamental laws of heat and energy, which state that order naturally decays into disorder. In our daily lives, things tend to get messy. A dropped egg breaks, but a broken egg never puts itself back together. A white hole seems to defy this natural flow by creating order out of chaos, concentrating energy, and throwing it outward. Many scientists think a white hole is simply too unstable to survive. The moment even a tiny speck of dust falls toward its boundary, the white hole could instantly collapse under its own weight, turning back into a black hole. Still, some researchers suggest that white holes did play a role in our cosmic history. They propose that when a black hole finishes collapsing, it might reach a quantum limit and bounce back, opening up elsewhere in space and time as a white hole. Some have even proposed that the birth of our own universe was actually the eruption of a white hole, pouring out matter into a new dimension. For now, these objects remain beautiful mathematical possibilities. They remind us that the equations of the cosmos are full of hidden paths, waiting for us to discover if they are real or just mathematical ghosts. The Higgs vacuum instability. Imagine a heavy wooden ball resting on a grassy hill. It is not at the very bottom of the valley, where it would be completely stable. Instead, it has settled into a small, shallow dip halfway down the slope. A tiny push, or even a strong gust of wind, could easily nudge it out of this temporary resting place. Once dislodged, the ball would roll all the way down to the true bottom of the hill, releasing all its energy as it goes. This simple image is one of the ways physicists describe the universe. Physicists believe our entire universe might be resting in a similar state of delicate balance. The culprit is the Higgs field, an invisible energy grid that fills every corner of space. This field is responsible for giving particles their mass. Without it, electrons and quarks would weigh nothing and fly apart at the speed of light. We would have no atoms, no chemistry, and no life. We tend to think of the vacuum of space as empty and stable, the lowest possible energy state. But calculations suggest that our vacuum might only be a false vacuum. Like that ball in the shallow dip, the Higgs field might be trapped in a temporary state of stability. The true bottom of the hill, the true vacuum, lies somewhere deeper, waiting for the field to slide down. In the quantum world, things do not always need a physical push to move. Quantum particles can tunnel through barriers, suddenly appearing on the other side of an energy wall. At any moment, in some random patch of the cosmos, the Higgs field could quantum tunnel through its energy barrier. If even a single point in space slips into the true vacuum, it would trigger a chain reaction, spilling the energy of the field outward. A bubble of true vacuum would form. This bubble would expand outward in all directions at the speed of light. Inside this bubble, the laws of physics would be completely rewritten. The Higgs field would become stronger, changing the masses of all particles. The fundamental forces that hold atoms together would dissolve. Chemistry, as we know it, would cease to exist. It would sweep across the cosmos, reshaping everything in its path. Because this bubble travels at the speed of light, we would never see it coming. There would be no warning, no flash of light, and no sound. One moment the universe is as it has always been, and the next, it is replaced by an entirely new reality. It is a quiet, instant cosmic reset. It is a transition so clean and fast that no observer could ever record it. This possibility feels unsettling, yet it highlights how temporary our universe might actually be. The very fabric of reality rests on a knife edge, waiting for a cosmic nudge. We exist in a cosmic pause, enjoying the warmth of a temporary valley, while the true depths of the universe wait in silence. Perhaps this instability is simply part of the cycle of space. Interstellar Objects. Imagine a dark, silent voyager sliding through the cold desert of our solar system. It is long and thin, shaped perhaps like a giant needle or a flat celestial stone, tumbling slowly through the dark. This strange traveler came from the vast space between the stars, entering our neighborhood at a speed so high that it could never be captured by the pull of our sun. We called it Oumuamua, a Hawaiian name meaning a messenger from afar arriving first. It was the first time we ever observed an object from another star system up close, and it did not behave like anything we expected. We are used to things that belong to our own solar family, but this was a true stranger, born under a different sun. As it passed near our sun, it did something that puzzled scientists. It began to speed up, pushed by some unseen force. When comets speed up like this, it is because the warmth of the sun boils their icy interiors, releasing jets of gas and dust that act like tiny rocket engines. This process creates a glowing tail, a bright shroud of dust that we can easily detect. Yet, even under our most powerful instruments, Oumuamua showed no signs of a tail. There was no dust, no gas, and no water vapor. It was completely dry and silent, yet it kept accelerating against the pull of gravity, defying our standard models of comets and asteroids. Some suggested it could be a giant hydrogen iceberg melting invisibly in the sunlight. Others proposed it was a fragment of a destroyed planet, or even a thin sail catching the gentle pressure of starlight. Because it was moving so fast, we only discovered it after it had already made its closest approach to the sun and was already rushing away from us, back into the deep dark of interstellar space. We had only a few short weeks to gather clues before it faded. This is the great frustrating challenge of studying these cosmic visitors. By the time we realize they are here, they are already leaving. We are left with fuzzy, distant data and must try to reconstruct their secrets from a handful of measurements. Where did this traveler come from? And how long has it been drifting in the lonely cold? Are there millions of these silent wanderers passing through our neighborhood entirely undetected? We may never know the answers for this particular visitor, as it is now far beyond the reach of our instruments, drifting back into the quiet ocean of stars from which it came, leaving behind only questions. Gravity weakness. Think about a simple refrigerator magnet. It is a tiny piece of metal, perhaps no larger than a coin, decorated with a picture or a simple design. If you place a small metal paperclip on a wooden table and hold the magnet just above it, the paperclip leaps upward, clinging to the magnet. In that quiet moment, a force you can hold between two fingers has defeated the gravitational pull of our entire planet. The Earth is 6 sextillion tons of rock, iron, and magma, all pulling downward on that tiny paperclip. Yet, the small magnet wins easily, holding the clip suspended in the air. This simple demonstration highlights one of the deepest mysteries in physics. Gravity, the force that keeps our feet on the ground and guides the planets in their orbits, is surprisingly weak. When we study the universe, we find 4 fundamental forces that govern everything we see. There is the strong nuclear force, which binds atomic nuclei together. There is the electromagnetism that powers our lights, holds molecules in place, and allows the magnet to lift the paperclip. There is the weak nuclear force, responsible for radioactive decay. And then, there is gravity. When physicists compare the strengths of these forces, the gap is mind-bending. Gravity is weaker than the strong nuclear force by a factor of 10 followed by 39 zeros. To help imagine this difference, if the strong force were the size of the entire visible universe, gravity would be smaller than a single atom. Why is there such a massive gap? This puzzle is known as the hierarchy problem, and it has baffled the greatest minds for decades. We do not know why gravity is so out of step with the others. In our daily lives, gravity feels powerful because we live near a massive body. It shapes our mountains, pulls on our muscles, and keeps the moon in orbit. But on the scale of individual particles, gravity is almost non-existent. Two protons repel each other electrically with a force that is vastly stronger than their gravitational attraction. In fact, gravity is so weak that it plays no role in how atoms bond or how chemistry works. To explain this bizarre weakness, some physicists have proposed a wild idea. They suggest that we are only seeing a tiny fraction of gravity. Perhaps our universe is a three-dimensional surface floating in a higher dimensional space. While electromagnetism and the nuclear forces are trapped on our surface, gravity might be free to travel. It might leak out into these extra hidden dimensions, diluting its strength before it reaches us. We are left with a quiet mystery. Is gravity inherently weak, or is it leaking away into spaces we cannot see? Until we can probe the smallest scales of space, we can only marvel at how a force so gentle can still hold the cosmos together. The Pioneer Anomaly. Imagine sending a message in a bottle out into the vast, quiet expanse of a dark ocean. You calculate exactly how the currents and the wind will carry it, predicting its path down to the fraction of an inch. But as you watch it drift away through your telescope, you notice something strange. The bottle is moving slightly slower than it should. It is as if some invisible hand is gently pulling it back toward the shore. This is exactly what happened in the late 20th century with two of our most famous space explorers, Pioneer 10 and Pioneer 11. Launched in the early 1970s, these robotic travelers were designed to fly past the outer planets and then keep going, heading out into the silent dark of interstellar space. They carried golden plaques designed to tell any passing alien civilizations who we are and where we live. But as the spacecraft coasted past Jupiter and Saturn, moving farther from the Sun than any machines before them, scientists noticed a tiny discrepancy in their speed. Both spacecraft were slowing down just a little bit too fast. Every year, they fell behind their predicted schedules by about 3,000 miles. In the grand scale of the solar system, 3,000 miles is almost nothing, a tiny fraction of a hair. Yet, to the physicists tracking them, this tiny drag was a giant mystery. It felt as though an unknown force, a weak gravity, was tugging them back toward the Sun. For decades, scientists debated what could be causing this Pioneer anomaly. Some proposed that we had discovered a flaw in our understanding of gravity, or perhaps some mysterious new property of dark matter. The answer, when it finally arrived, was far more ordinary, yet beautiful in its complexity. The spacecraft were powered by small nuclear generators. These generators produced heat, and that heat radiated out into the cold void of space. Because of the way the probes were built, more heat escaped from one side than the other. Like a tiny, invisible rocket engine, this escaping heat pushed back against the spacecraft, slowing them down. It was a recoil force, so faint that it took decades of computer modeling to prove. This long mystery reminds us of how difficult it is to measure physics in the deep dark. When we send our machines into the great unknown, even the heat of their own robotic bodies can alter their path. It reminds us that in space, the smallest details matter. Supermassive black hole origin. Imagine looking back to the very dawn of time, shortly after the cosmos burst into existence. We look through our most powerful instruments, expecting to see a young, simple universe, perhaps containing small baby stars and tiny, forming galaxies. Instead, we find something that seems completely impossible. We discover gargantuan, supermassive black holes, each containing the mass of billions of suns, already sitting quietly at the centers of ancient galaxies. These giants existed when the universe was only a few 100 million years old. How could objects so massive form in such a short amount of time? To understand why this is a mystery, we have to look at how black holes grow. A black hole cannot simply eat as fast as it wants. As a black hole pulls matter in, that matter spirals around it, rubbing against itself and heating up to extreme temperatures. This superheated material glows with brilliant light, releasing immense amounts of energy. This energetic radiation pushes outward, actively fighting against the inward pull of gravity. This cosmic balancing act is known as the Eddington limit. It acts as a speed limit for feeding black holes. If a black hole feeds too fast, the light it produces pushes its food away, stopping the growth. Even if a black hole fed at this maximum speed non-stop from the very beginning of time, it could not have grown from the size of a collapsed star into a monster of billions of solar masses in just a few 100 million years. There simply was not enough time. This puzzle has forced scientists to think of other possibilities. One idea is called direct collapse. Instead of a normal star dying and leaving behind a small black hole, a massive cloud of gas containing the weight of 100,000 suns might have collapsed directly under its own weight. This skip-the-middleman process would create a giant baby black hole right from the start, giving it a massive head start in its growth. Another idea is that these giants grew in dense environments where they merged with other black holes repeatedly. Or perhaps they fed on dense streams of cold gas that bypassed the radiation limit. But every theory we have still struggles to explain the sheer size of the oldest black holes we observe. Recently, modern space telescopes have looked even deeper into the past, finding even more of these early giants. These observations are forcing us to rewrite our understanding of how the first structures in the cosmos formed. The timeline we built over decades is now being questioned. We are left with a profound question. Did the first stars shape the galaxies, or did these silent giants act as the seeds around which everything else was built? The proton decay. If you hold a glass of water in your hand, you are holding trillions of tiny building blocks called protons. These little particles sit at the very center of every atom, forming the bedrock of everything we can touch, see, and feel. We often think of them as permanent, the eternal building blocks of the universe. But physicists have proposed a quiet, unsettling idea. They suggest that these fundamental particles might not last forever. Instead, they might slowly, silently fall apart, decaying into even smaller particles over periods of time that are almost impossible to imagine. In the physics of the very small, there are rules about how particles behave. For a long time, we believed that protons were completely stable, that they would outlast the stars themselves. Then, scientists began searching for a single theory to unite all the forces of nature, a grand unified theory. When they wrote down the mathematics for this grand unification, they discovered something unexpected. The equations showed that the proton should have a finite lifetime. It should eventually break apart. If this idea is correct, then all the matter in the universe has an expiration date. Every star, every planet, and every living being is made of pieces that are slowly ticking down. Eventually, in the deepest, coldest future, everything we know could dissolve into a thin mist of light and radiation. To test this theory, scientists built a massive experiment deep underground in Japan, inside an old mine, shielded from the noisy cosmic rays of space. It is called Super Kamiokande. The experiment consists of a giant cylinder filled with 50,000 tons of pure water, surrounded by thousands of light detectors. The idea is simple. Because there are so many protons in that water, if even one of them decays, it will release a tiny flash of light. Scientists sit in the dark, waiting for a single flash that has never been seen. So far, the detectors have recorded nothing. No proton has ever been observed falling apart. This silence tells us that if protons do decay, they must live for an unimaginably long time. The current limit suggests a proton must live for at least 10 to the power of 34 years. To put that into perspective, the universe itself is only about 13.8 billion years old. That is a 1 followed by 10 zeros. The minimum lifetime of a proton is a 1 followed by 34 zeros. This leaves us with a profound mystery. Is the proton truly immortal, a permanent foundation for the universe? Or are we simply living in the very brief morning of a cosmos that will slowly dissolve into nothingness? We do not know if the ground beneath our feet is eternal, or if it is slowly slipping away, one silent particle at a time. The universe may look stable today, but it might just be aging so slowly that we cannot see the change. Cosmic string networks. Think of walking across a frozen lake in the middle of winter. Under your feet, the ice is not perfectly clear. It is filled with white lines, fractures, and long, jagged cracks that became trapped in the structure as the liquid water cooled and turned to solid ice. These lines are imperfections, places where different sections of ice met and did not align perfectly. Scientists believe something very similar might have happened to the universe itself during its earliest moments. When the hot, energetic infant universe began to cool down rapidly, it underwent phase transitions, much like water freezing into ice. During this cosmic cooling, the very fabric of space and time might have cracked. These cracks are what we call cosmic strings. A cosmic string is a hypothetical defect in the structure of the universe. They are not like normal strings made of atoms. Instead, they are one-dimensional lines of pure energy, thinner than a single proton, yet stretching across millions of light years. Because they are so thin and packed with the intense energy of the early universe, they are unimaginably heavy. A single mile of a cosmic string could weigh as much as the entire Earth. If these strings exist, their extreme gravity would do strange things to the space around them. Imagine a straight line cutting through space. If you were to wrap a circle around this line, you would find that the circle does not have 360 degrees. The cosmic string actually cuts out a small wedge of space, pulling the remaining sides together. Because of this warping of space, light traveling past a cosmic string behaves in a very unusual way, bending around the defect as if it were a massive lens. If a cosmic string lies between us and a distant galaxy, the light from that galaxy will bend around both sides of the string. Instead of seeing one galaxy, we would see two identical copies of the same galaxy right next to each other, separated by a tiny angle. This is a special type of gravitational lensing. Astronomers search the deep sky for these twin galaxy pairs, looking for perfect duplicates that might reveal the presence of an invisible cosmic string stretching across the dark. We have not found them yet. The search requires scanning massive amounts of astronomical data, looking for these subtle cosmic mirages. If we do find one, it would be a direct link to the very beginning of time, a fossilized scar from the birth of our universe, helping us understand the forces that shaped everything we see today. Until then, these silent, invisible threads remain one of the most intriguing possibilities of the cosmos. The lithium problem. Imagine baking a loaf of bread using a recipe passed down for generations. You measure the flour and the water, and they turn out exactly right. But when you add the final pinch of salt, the final taste is completely wrong. This is the puzzle cosmologists face when they look at the oldest elements in our universe. It is a quiet mystery known as the lithium problem. During the first few minutes after the Big Bang, the entire universe was a hot, dense soup of energy and particles. As space expanded and cooled down, protons and neutrons began to bind together. This era is called Big Bang nucleosynthesis. It was the brief moment when the very first atomic nuclei were forged. Our mathematical models of this period are highly precise. They tell us exactly how much hydrogen, helium, and lithium should have been created in that cosmic furnace, leaving behind a clear chemical fingerprint. When we measure the amounts of hydrogen and helium in the oldest, most pristine stars, the numbers match our calculations perfectly. The cosmic recipe works. But when we look at lithium-7, the calculations break down. Our theories predict there should be 3 times more lithium-7 in these ancient stars than we actually observe. The stars seem to have far less lithium than they should, leaving a massive gap in our understanding. Where did the missing lithium go? There are 2 main directions physicists look to find an answer. The first idea suggests we might have made a fundamental mistake in our calculations of the nuclear reactions that occurred during the first minutes of time. Perhaps some unknown process destroyed the lithium before the first stars ever formed. Or maybe there is a gap in our current knowledge of nuclear physics under extreme conditions. The second idea points to the stars themselves. The oldest stars have lived for billions of years. Over these vast stretches of time, the material inside a star might have mixed in ways we do not fully comprehend. The lithium at the surface of a star could have been slowly carried down into the deep, hot interior, where it was burned away by stellar fusion. Alternatively, perhaps we do not fully understand the atmospheres of these ancient stars, leading to incorrect measurements. This leaves us with a choice between 2 possibilities. Either we do not understand the physics of the early universe as well as we think we do, or we do not fully understand how stars behave over billions of years. Both options are exciting. They remind us that even our most successful theories still have gaps, waiting for a new discovery to fill them. Dark sirens. Imagine sitting in a quiet room, listening to the faint, low hum of a distant collision. Far out in the dark ocean of space, 2 massive dead stars are spinning around each other, drawing closer and closer until they crash. We cannot see this crash with our telescopes. No light escapes the event, and no heat reaches our detectors. Yet, we can hear it. The collision sends out tiny ripples that stretch and squeeze the fabric of space itself. These ripples travel billions of light years across the universe, eventually passing through our planet and gently vibrating our detectors. By listening to these cosmic sounds, scientists are trying to build a new map of the cosmos. These ripples are known as gravitational waves. They are different from sound waves traveling through air, acting instead as actual distortions in the fabric of space and time. When massive objects like black holes or neutron stars collide, they shake the universe, creating waves that travel at the speed of light. When these collisions happen without producing any light, astronomers call them dark sirens. Just as a lighthouse horn tells a ship how far away the shore is by how loud the sound is, these dark sirens can tell us how far away they are. The shape and pitch of the gravitational wave tell us exactly how energetic the collision was. By comparing how energetic the crash was to how faint it feels when it reaches us, we can calculate the distance to the collision. Astronomers hope to use these dark sirens to resolve our current measurement conflict regarding how fast the universe is expanding. It is a completely independent way of measuring the cosmos, free from the assumptions of older methods. However, using these dark sirens is not simple, and many uncertainties remain. To convert a wave signal into a precise distance, we must know the angle of the collision. If we view it from the side, the signal seems weaker, making it appear much farther away. Furthermore, without a flash of light to pinpoint the exact galaxy where the crash happened, we must guess which galaxy in a crowded field is the true home of the siren. To make this method work, researchers must gather a large catalogue of these faint signals. Each new detection acts like a single puzzle piece, slowly filling in our picture of the expanding universe. If we can collect enough of these quiet whispers from the dark, we might build a bridge across the gaps in our current understanding. For now, we wait and listen, capturing the faint tremors of ancient cosmic collisions, hoping they will tell us the true scale of our universe. We do not yet know if this new method will finally bring agreement to our measurements of cosmic expansion, or if it will open up new mysteries we have yet to comprehend. Time asymmetry. Imagine holding a ceramic cup in your hand. If you let it go, it drops to the floor and shatters into dozens of tiny pieces. The event is simple, ordinary, and entirely permanent. If a recording of this event were played backward, it would feel completely wrong. Scattered fragments would slide across the floor, come together, rise into the air, and mend themselves back into a perfect cup in your hand. We know this never happens in real life. Yet, if we look closely at the fundamental laws of physics that govern the movement of every single atom in that cup, we find a deep mystery. The equations that describe how particles bounce, slide, and interact do not care about the direction of time. If you run the mathematics of a single collision backward, the math works just as perfectly as it does forward. At the level of individual particles, time has no preferred direction. The laws of nature are symmetrical. Why then, when we put trillions of these particles together to make a cup, does time suddenly develop a strict, one-way path? This puzzle brings us to a concept known as entropy, which is often described as a measure of disorder. The second law of thermodynamics states that in any closed system, the overall entropy or disorder must always increase over time. When the cup is whole, it is in a highly organized state. The atoms are arranged in a very specific, orderly structure. When the cup shatters, those atoms scatter into countless chaotic arrangements. There are trillions of ways for the pieces to lie broken on the floor, but only one very specific way for them to fit together to form a whole cup. Because there are so many more disordered states than ordered ones, the system naturally moves toward disorder. It is a matter of probability. But this explanation leads to a much deeper question. If the universe is constantly moving from a state of order to a state of disorder, it must have started in a state of extremely high order. We must ask why the early universe, right at the moment of the Big Bang, began in such a highly organized, low entropy state. If the universe had started in a state of maximum chaos, stars would never have formed, galaxies would never have gathered, and life would never have begun. The arrow of time that we experience every day is actually a lingering echo of that pristine order at the dawn of creation. Why the cosmos began in this way remains one of the greatest unsolved mysteries in physics. Some scientists suggest that our perception of time flowing forward is not a fundamental property of the cosmos at all. Instead, it might be an emergent property, a kind of illusion that only appears when we look at things on a large scale. While a single water molecule is dry on its own, a collection of billions of them feels wet to the touch. In a similar way, time might only exist when we observe the collective behavior of massive numbers of particles. In the quiet depths of the quantum world, time as we know it might not exist at all. Dark flow. Imagine standing on the shore of a vast, misty ocean at night. Out on the water, a group of small boats drifts slowly. They are not drifting randomly in different directions as you would expect from the local winds. Instead, every single boat is moving in the exact same direction, pulled by a silent, powerful current. You gaze out toward the horizon, but you cannot see what is causing this movement. The source of the current lies far beyond the limits of your vision, hidden in the deep darkness. We can only watch the steady drift and realize that something massive is pulling them from the shadows. This image helps us understand a mystery that has puzzled astronomers for years. When we study the universe on a grand scale, we expect galaxies and clusters of galaxies to move apart from each other because of the expansion of space. However, when researchers began measuring the movement of massive galaxy clusters, they found something unexpected. A large number of these giant structures, containing thousands of galaxies, seem to be drifting together toward a specific patch of the sky. They are moving at a speed of more than 2 million miles per hour. This collective migration is what scientists call dark flow. This movement is different from the local gravitational pull of nearby objects. This is a massive cosmic current that spans billions of light years. It suggests that something outside our observable universe is pulling on everything we can see. Because the light from beyond our observable horizon has not had enough time to reach us since the beginning of time, we cannot observe whatever is causing this pull. It is a force operating in the dark, acting on our universe from a place we can never visit or view directly. Many scientists are skeptical about this discovery. They argue that the measurements are exceptionally difficult to make, and that the apparent drift might be nothing more than statistical noise or errors in data analysis. When other teams tried to replicate the study, some found the same flow, while others found no evidence of it at all. The debate remains open, and the data is still being analyzed. It is a reminder of how difficult it is to measure the cosmos when we are trapped in our own tiny corner of it. If this giant cosmic current is real, the implications are unsettling. It would mean that our observable universe, everything we can see with our most powerful telescopes, is just a small part of a much larger space. It would mean that massive structures exist far beyond our horizon. Structures so large they can pull entire families of galaxies across the cosmic divide. We are left watching the horizon, observing the slow drift of the stars, and wondering what giant shape is waiting for us in the dark. Galactic magnetic fields. If we had the ability to detect magnetic forces directly, our galaxy would appear entirely different. Instead of a flat disk of stars, we would perceive giant, glowing ropes of energy wrapping around the spiral arms, curving like a vast cage of invisible threads. These are galactic magnetic fields. They are silent, invisible forces that gently nudge the path of cosmic dust and channel the flow of gas. For a long time, we believed gravity was the only architect of the cosmos. We believed gravity pulled gas clouds together, ignited stars, and spun galaxies into beautiful spirals. However, when scientists calculated the strength of gravity alone, the math did not add up. Gravity is not strong enough to keep the beautiful spiral arms of a galaxy from flying apart or falling into chaos over billions of years. Something else is helping to hold the structure together, acting like invisible cosmic scaffolding. That helper is magnetism. These galactic magnetic fields are extremely vast, stretching across hundreds of thousands of light years. Yet, they are weak, millions of times weaker than the magnet sticking to a kitchen refrigerator. Even so, across the vast emptiness of space, this faint force accumulates. It shapes where new stars can be born by preventing gas clouds from collapsing too quickly. It also guides the pathways of cosmic rays, which are high-energy particles traveling near the speed of light. But where did this magnetism come from? This is one of the great mysteries. Some scientists think these fields started as tiny seeds of magnetic energy created shortly after the birth of the universe. Over billions of years, the slow rotation of galaxies acted like a giant dynamo, spinning and stretching these tiny seed fields, amplifying them into the massive structures we observe today. Others believe the fields were generated later by the movement of charged particles within the very first stars and active black holes. We cannot observe these fields directly, but we know they exist by measuring how they affect light. When radio waves travel through space, they vibrate in specific directions. As these waves pass through a galactic magnetic field, the field gently rotates the direction of that vibration. This effect is known as Faraday rotation. By measuring this subtle twist in the radio signals from distant objects, astronomers can map the invisible magnetic shape of our universe. We are left with a quiet realization that the empty spaces between stars are not empty at all. They are filled with a delicate, pulsing web that connects the smallest particles to the largest structures in the cosmos, a silent force whose origin remains hidden in the deep past. The origin of life. Imagine a warm, mineral-rich pool on an ancient volcanic island 4 billion years ago. The sky above is a thick haze of carbon dioxide, and the ground is made of dark, barren basalt. In this quiet pool, simple carbon-based molecules bounce against one another, driven by the gentle heat of the Earth. Over countless random collisions, a quiet transformation occurs. A few of these basic chemical pieces link together, forming a chain that can attract other pieces and build a copy of itself. For the first time in the history of our world, chemistry becomes biology. This is the moment life begins, yet the exact path of this transition remains one of the deepest, most quiet mysteries in all of science. For a long time, researchers have focused on a concept known as the ribonucleic acid world. In modern organisms, deoxyribonucleic acid holds the genetic instructions, while proteins do the physical work of the cell. But deoxyribonucleic acid needs proteins to replicate, and proteins need deoxyribonucleic acid to be built. It is a classic circle of cause and effect. Ribonucleic acid is a molecular cousin that can both store information and perform physical reactions. The idea is that early life relied entirely on this single molecule to carry out both jobs. Yet, this idea has its own hurdles. Ribonucleic acid is a delicate, complex molecule. Making its components in a messy, primordial environment is difficult, and scientists still struggle to explain how these fragile pieces could have assembled themselves without a living cell to guide them. This has led researchers to point to different environments where this spark might have occurred. Some point to the dark depths of the ocean, where hydrothermal vents spew hot, mineral-laden water into the cold sea. These vents have tiny, rocky pockets that could act as natural chambers, concentrating molecules and providing the energy needed to drive early reactions. Others focus on shallow volcanic clay beds on land. Here, cycles of wetting and drying could help link smaller pieces into longer chains, using the clay surface as a scaffolding. In these quiet pools, wet periods bring new ingredients together, while dry periods allow them to bond and grow. We are left to contemplate whether this transition was an inevitable result of cosmic chemistry or a rare accident. If you mix the right ingredients under the right conditions, does life simply emerge as a natural property of the universe, like the formation of crystals or stars? Or was it a sequence of events so specific and unlikely that it has occurred only once on this single blue planet? If it is a natural law, then the universe may be teeming with life, waiting to be found. If it is a rare accident, then our existence is a fragile light in a vast, silent dark. If life can begin, what happens when the very universe we inhabit expands so much that we can no longer see the cosmos? The end of observation. Imagine the night sky 100 trillion years from now. By then, the stars of our Milky Way and its closest neighbors will have merged into one giant glowing island of aging stars. Outside of this island, there is only an endless, absolute dark. If an astronomer were living in that distant epoch, they would point their most advanced telescopes into the deep void and find absolutely nothing. No distant spiral shapes, no faint glows of faraway clusters, no ancient beacons of light. The entire universe beyond their own galaxy would have completely vanished. This silent isolation is the result of the constant, accelerated expansion of space. With every passing second, the gaps between galaxy clusters grow wider and wider. Eventually, this expansion will happen so fast that light from other galaxies will never be able to cross the distance to reach us. They will slide past our cosmic horizon, disappearing forever into the unobservable zone of the universe. They have not ceased to exist. Instead, they have been carried away by the expanding fabric of space, moving faster than light can travel. This leads to a quiet, philosophical tragedy of knowledge. Future civilizations will grow up under a lonely, dark sky. They will build telescopes, scan the heavens, and conclude that their single, solitary galaxy is the entirety of existence. They will have no way of knowing that space is expanding. The essential evidence we rely on today to understand our cosmic history will be gone. The cosmic microwave background, the ancient echo of the birth of space and time, will have stretched so thin that it will be completely undetectable. The red shifting of distant starlight, which showed us that galaxies are rushing away from each other, will no longer exist because there will be no other galaxies to observe. These future scientists will construct a cosmology that is neat, logical, and entirely incorrect. They will look at their quiet, dark sky and believe that the universe has always been static, unchanging, and confined to their own local group of stars. They will have no reason to search for a beginning, because all clues of that beginning will have been erased by the stretching of space. It is a humbling thought that we live in a very specific, privileged window of time. Today, the universe still carries the clear clues of its infancy. We can still see the light of ancient stars, measure the leftover warmth of the early universe, and map the giant cosmic web. We are fortunate enough to live in a season of cosmic history where the past is still written in the sky for us to read. One day, that library will close and the pages will go blank. We are left to wonder what other secrets of the cosmos have already slipped beyond our horizon, lost to the past before we ever had the chance to look.